Hello. Uh, Today we will discuss some basic definition in optical isomerism. Uh, in last class, after the last class, we have discussed the chiral carbon, chiral compound, symmetry point, and R and S configuration in different projection. In flying wedge diagram, in Fisher projection, we have discussed all of this. So some of the basic definition is still left. Let's start with the discussion. First definition we need to discuss is enantiomer. Enantiomer. What are enantiomers? See, if you are having two optically active compound which are mirror images of each other. Two optically active compound which are mirror images of each other are known as enantiomer. And in enantiomers are having some property, their physical and chemical properties of enantiomers are same, right? And if two different compounds are having same physical and chemical property, if you want to separate them, it will be very difficult. So it is said that when we two enantiomers cannot be separated even by fractional distillation. For the enantiomers, we can note down that there is only one property which is different. Their behavior towards plane polarized light is different. Enantiomers are having different behavior towards plane polarized light. Let's write the definition first, then we will discuss. Optically active compounds. Optically active compounds which are mirror images of each other, which are mirror images of each other, are known as each other, are known as enantiomers. Enantiomers. Some important points about this is the physical and chemical properties. Physical and chemical properties of enantiomers. Enantiomers are same, except their behavior towards plane polarized light. In short, it is PPL. So if their physical and chemical properties are same, they cannot be separated. They cannot be separated by fractional distillation method. Fractional distillation method. So let's take an example. First copy these points, then I'll explain each and every points. One example for this. Let's say I have a compound which is containing only one chiral carbon. We have already discussed about that. If a compound is containing only one chiral carbon, it is going to be optically active. So there is only one chiral carbon. This compound is going to be optically active. Just take the mirror image of this compound. We are going to draw the mirror image of this compound. Fluorine will be definitely on left hand side in mirror image, hydrogen will be on right hand side. Mirror image compound is also going to contain one chiral carbon. This is optically active. Original compound is also optically active. These two are known as, pair of these two compounds are known as enantiomers. Remember, enantiomers are in pairs, right? A single compound cannot be enantiomer, right? So what I am saying, if these two are enantiomers, their physical and chemical properties are same except their behavior towards plane polarized light. Except their behavior towards plane polarized light. We can find the configuration of this chiral carbon also. We have already discussed to assign the configuration R or S. We have already discussed. Fluorine is having first priority here. CH3 is of second priority. Deuterium third priority. And hydrogen is of fourth priority. Lowest priority is on horizontal line. Start moving from first priority to second priority and then second priority to third priority. If you are moving in anti-clockwise direction, the configuration is going to be R. Remember the rule, if lowest priority is on vertical line and on moving first priority to second priority, then second priority to third priority. If you are moving in clockwise, it is R. Anti-clockwise S, when lowest priority is on vertical line. And if the lowest priority is on horizontal line, on moving first priority to second priority, then second priority to third priority. If you are moving in anti-clockwise direction, it is R, otherwise it is S. So if the configuration of chiral carbon in original compound is R, you are taking the mirror image. We have also discussed one property that on taking the mirror image, configuration of chiral carbon gets inverted. So configuration of chiral carbon in the mirror image is going to be S, right? Now next, what I am saying, their behavior towards PPL is different. It means if our original compound is dextrorotatory, let's say our original compound is dextrorotatory, that means this compound is rotating the PPL in clockwise direction. This compound is rotating the PPL, right? PPL it is not related with the configuration. Remember, dextro and levo property of an optically active compound is not related with the configuration of chiral carbon, right? Dextro and levo properties are practical properties which can be determined only by doing practicals. So what I am saying, just assume that our original compound is dextrorotatory, it is rotating the PPL in clockwise direction, then definitely our mirror image is going to be levorotatory, right? If it is dextro, if original compound is dextro is represented by small d, then definitely our mirror image is going to be levorotatory. And if it is happen that our original compound is levorotatory, then our mirror image of this compound will be dextrorotatory. Properties are different towards plane polarized light. If one compound is dextrorotatory, another compound is going to be levorotatory. This is the only property which is different in case of enantiomers. Now, if you want to separate this compound, suppose I have a mixture of this compound. These two compounds are taken in one beaker and you want to separate them. You cannot separate them by using normal distillation or fractional distillation method. What is the fractional distillation method and normal distillation? If you remember, if you done some practicals, so you might have observed that such type of apparatus is there in laboratory. You have a mixture of compound, then just heat it, and one condenser is connected like this, and then we are going to cool the vapor which is formed and collecting one component over here. This setup is normal distillation. This is condenser, right? This setup is normal distillation. I have a mixture of two compounds, let's say A and B, two compound A and B. if the boiling point of these two compounds A and B are same, exactly same, what I am saying, their physical properties are same, so their boiling point, their melting point, all are going to be same. If the two compounds are having same boiling point, you cannot separate them by using normal distillation, because when you are going to heat the mixture, both the compound will get converted in vapor phase simultaneously, and both are going to have same tendency to convert in vapor phase. So again, when you are going to condense the vapor, you will get a mixture of A and B. You cannot separate them. This is the normal distillation. And fractional distillation method, fractional distillation apparatus is slight different, in that we are having some more flask like this. This type of apparatus you must have seen in laboratory, and then again condenser is connected, and we are going to collect one of the component. So this type of apparatus is known as fractional distillation apparatus. And if you are going to heat the mixture A and B over here, again the same difficulty you will face, that if both the compound have same tendency to get converted in vapor phase, again when you are going to condense the vapor, the mixture of A and B will be obtained. That means you cannot separate A and B if their boiling points are same. See, in normal distillation method, if the two compounds having their boiling point differ by more than 20 degrees centigrade, we are using normal distillation method. If the two compounds having their boiling point difference less than 20 degrees centigrade, we prefer to use this fractional distillation method. But what about the case if the two compounds are having exactly equal boiling point? In case of enantiomers, they cannot be separated even by using fractional distillation method. That you should remember, and it is very important. It is directly asked in exam also, that fractional enantiomers can or cannot be separated by fractional distillation method. And remember also, if our original compound is dextro, its mirror image is going to be levorotatory. If original compound is levorotatory, then its mirror image is going to be dextrorotatory. There only one behavior is different, and that is behavior towards plane polarized line, right? This was the first definition. Now the second definition that we need to discuss is dextrorotatory. Dextrorotatory. Sorry, not dextro. Diastereomer. Diastereomer. What are diastereomer? See what I am saying. In diastereomer, just observe the definition word by word, because there are situations, there are some questions. If you are not very careful about the definition of diastereomers, you may get dhokha, right? So diastereomer definition is stereoisomers which are not the mirror images of each other, not the mirror images of each other, are known as diastereomer. Some important point, the physical and chemical properties of diastereomers are different. Diastereomers are different, and they can be separated. They can be separated by distillation method. They can be separated by distillation method. Just because their physical and chemical properties are different, their boiling point will also be different. So two compound can be separated if their boiling points are different. Now in definition that I was saying, you must focus on each and every word. First word is stereoisomers. Remember, in previous case, in the definition of enantiomers, it was written optically active compound. Optically active compound, if it is optically active, then definitely it is included in optical isomerism. But if it is said stereoisomers are divided in two parts, that is geometrical and optical. What I am trying to say is diastereomers can also be geometrical isomers. Remember, diastereomers can also be geometrical isomers, because in definition it is said stereoisomers, which includes geometrical isomers and also optical isomers, which are not the mirror images of each other, are known as diastereomers. Their physical chemical properties are different. Their physical chemical properties are totally different, and of course if their properties are different, they can be separated by distillation method. Let's see the example. Let's see one of the example. Let's say I have a compound like this. Compound is containing, let's say, 2 chiral carbon. HNOH is attached on chiral carbon. It is having 2 chiral carbon. Next, I can draw one more compound with the same molecular formula. Of course, with the same molecular formula, I am going to change the configuration only at 1 chiral carbon. That means if you are changing the position of atom or group of atom around a chiral carbon in space, it is going to generate stereoisomers. So these two are enantiomers. These two are stereoisomers. Definitely their molecular formula are same, their structural formula are same, but they are not the mirror images of each other. If these two are not the mirror images of each other, but these two are stereoisomers, definitely pair of these two compounds are said to be diastereomers. These two are diastereomers. Diastereomers. Their physical and chemical properties are different. Their physical and chemical properties are different. Now, one example I also want to give you. One more example. Let's see one more example. Suppose I have cis-2-butene, and next what I am drawing is trans-2-butene. If it is asked what is the relation between cis-2-butene and trans-2-butene, and in option they are not mentioning geometrical isomers, they are mentioning enantiomers, diastereomers, identical, none of these such type of options are given. So remember, geometrical isomers are also stereoisomers. Stereoisomers which are not the mirror images, definitely cis and trans are not going to be the mirror images of each other. So these two are also known as diastereomers. Geometrical isomers are also going to be diastereomers. These two are also diastereomers, right? I hope it is clear to you the definition of diastereomers and enantiomers and their properties. Diastereomers are having different physical and chemical properties, while enantiomers are having same physical chemical properties except their behavior towards PPL. And we can identify the pair of diastereomer and enantiomers. Enantiomers are mirror images of each other, but diastereomers are not the mirror images of each other. There are so many questions asked in examination that what they are going to do, they are going to give you two compounds and they will ask what is the relation between these two compounds. This is very common question that can be asked in examination, and the option will be given again same, diastereomers, enantiomers, identical. One more thing, what are identical compounds? I have already mentioned you, I have already explained you what are identical compounds. If you are having two organic compound and both are having same IUPAC name, both two compounds are having same IUPAC name, including their configuration, then such type of compounds are known as identical compound. If the two compounds are having same IUPAC name, including their configuration, if any, configuration may be around double bond or around chiral carbon, then that two compound will be known as identical compound. I hope it is clear, because we have done some problem. We have identified the identical compounds while calculation of number of geometrical isomers. I hope you remember that, right? So let's do some problem on that. Let's do some problem. The language of problem is identify the pair of diastereomers, enantiomers and identical compound. Question is identify pair of enantiomer, diastereomer and identical compound, from the following. I'm going to give you some compound. What you need to do, you just need to identify the pair of enantiomers, diastereomers and identical compound, and it is going to be very, very interesting. Such type of questions are also asked very frequently in examination. Let me draw the structures. Suppose I have CS3. I am taking the case in which compound is having two chiral carbon, HOH. This is the first compound. Now the second compound is, let's do the slight change. CS3, OH, not OH, let's write here H and OH on right side. H and OH. Third compound, let's make bit complicated. CS3, OH. Fourth compound, bit more interesting, OH, CS3 and CS3, H, OH and H. Next, fifth compound is like OH, H, CS3 and OH, CS3. Sixth compound is it is something like let's say H and H, CS3, OH and OH. Now seventh compound, let me draw the last structure. Let's say I have OH on bottom side, H on above side. It is CS3 and OH and CS3 and H. These are 7 compounds. We need to identify the pair of enantiomers, diastereomers and identical compound in these. See, let's try to understand the processor, how we are going to proceed. One thing you should keep in your mind, that if you are going to take the mirror images now, then definitely the configuration of chiral carbon will get inverted. On taking mirror images, the configuration of chiral carbon is going to be inverted. Let's say I'm selecting the first compound and then comparing with any another compound. And we are looking for enantiomers. If you are looking for enantiomers, what you need to do, just find the configuration of chiral carbon in the first compound. Just find the configuration of chiral carbon in the first compound, and then let us say first carbon is having R configuration and second configuration is having S configuration, right? And if you are taking the mirror images, if you are going to take the mirror image of this compound, then configuration will get inverted. RS will get converted to SR, right? If the configuration is inverted with the same molecular formula, same structural formula, that two compound is going to be enantiomers. That two compound is going to be enantiomers. Be very, very careful. So keep in mind, if you are having a compound containing two chiral carbon and both the chiral carbon is having configuration RR, then its enantiomers will be having configuration SS. If the original compound is having configuration SS, then its enantiomer is going to have the configuration RR, right? And if you are looking for diastereomers, what is going to happen? If you are having two chiral carbon, right? If you are having two chiral carbon and in original compound, both the chiral carbon is having configuration R and R, then search for the compound in which one carbon is having same configuration while another carbon is having inverted configuration. Suppose you are having a compound in which both the chiral carbon is having configuration RR and next compound is having configuration RS. Definitely these two can never be mirror images. Reason, if you are going to take the mirror image, configuration of each and every chiral carbon will get inverted. If you are having configuration of two chiral carbon in original compound SS and another compound is having configuration SR, these two cannot be the mirror images. These two are going to be what? These two are going to be diastereomers. The only condition that their molecular formula and structural formula must be same, right? And what about identical compound? Identical compound, let's say I am having configuration RR in original compound and in another compound again you are going to get the configuration RR, right? So both are having same configuration, same molecular formula, same structural formula, it is going to be identical compound. So overall what you need to do in all the compound, you need to find the configuration of chiral carbon. Then only you can identify which pair is going to be enantiomer, which pair is going to be diastereomer, and which pair is going to be identical. Let's start. In first compound, if I want to find the configuration of first chiral carbon, definitely OH is having first priority around first chiral carbon, and then this whole group is attached with the first chiral carbon. This whole group is going to have second priority. This CH3 is going to have third priority. This hydrogen is going to have fourth priority. Least priority is on horizontal line. Start moving first priority to second priority and then second priority to third priority. You are moving in anti-clockwise direction. Anti-clockwise direction, lowest priority on horizontal line, the configuration is R. The configuration of this chiral carbon is R. Now, next, if you want to find the configuration of chiral carbon, second chiral carbon, what you need to do? Again, OH here also is having first priority, hydrogen is having second priority, this CH3 is going to have third priority, and this whole group is going to have second priority. Again, you start moving from first priority to second priority, then second priority to third priority, right? This is fourth priority, no? This is fourth priority. First priority to second priority to third priority. You are moving in clockwise direction, and lowest priority, that is the fourth priority, is on horizontal line. So the configuration of this chiral carbon is going to be S. First compound, the configuration of chiral carbon is R and S, right? Similarly, you can find the configuration of second compound if you closely observe. If you closely observe first and second compound, these two are mirror images of each other. First and second compound are mirror images of each other. So if the configuration of first chiral carbon in first compound is R, then the configuration of first chiral carbon in second compound is going to be S, just because it is mirror image. Similarly, here it is going to be R. Now, next. Just think and tell me what is the relation between first and second. Generally, what happened, beginners are going to say these two are mirror images. So, these two are what? Enantiomers. But wait a minute. What I am saying, this compound is completely symmetrical. This compound is completely symmetrical, and if you are going to do the IUPAC numbering, if you are going to write the IUPAC name, based on the configuration of chiral carbon, there is no such rule to give the priority. So I can do the numbering of this compound from top side or bottom side. I am free for that. If I am numbering this compound from bottom side, what will be the name? The configuration at second carbon, I am doing the numbering from bottom side. It is 1, 2, 3, 4. At second carbon, configuration is R, and at third carbon, configuration is S. What can I write the name? I will write the name 2R, 3S. It is 2R, 3S. Then butane, root word is butane 2,3-diol. It is butane 2,3-diol, right? Now, if you do the IUPAC numbering of first compound, and again what I am saying, again we are free to do numbering from any of the end. You can do the numbering from top side, you can do the numbering from bottom side. The compound is completely symmetrical. The OH group is present in second and third carbon, and on the basis of configuration of chiral carbon, there is no such rule to give the priority. So what I am going to do, I am going to do the numbering in first compound from top side. If you will do that, you will get R configuration on second carbon and S configuration on third carbon, and the IUPAC name will be same. It is 2R, 3S, butane 2,3-diol. Again you are getting the same name. What I was discussing, that if two compounds are having same IUPAC name, if two compounds are having same IUPAC name, that two compounds are going to be identical, right? So first and two compounds are identical. If I need to look for the identical compound pair, so it is first and second compounds are identical. Now, when it can happen that the compounds seems to be mirror images of each other, but they are not enantiomers. When this is going to be happen? This is going to happen only in case, listen very carefully, this can happen only in case the compound is completely symmetrical. That means compound can be divided in two equal parts. Compound can be divided. I can divide this compound into equal part, right? Compound can be divided into equal part, and one of the chiral carbon is having R configuration, while another chiral carbon is going to have S configuration. If the situation is that, in that case, definitely if you are going to take the mirror image, you are going to have the identical compound. I am repeating again. If it seems that these two compounds are mirror images and they are not enantiomers, this is going to happen only in one case, and that case is if compound can be divided in two equal parts and it is containing two chiral carbon, and both the chiral carbons are having different configuration. One is R while another one is S. Similarly, here also it is S and R. If we are going to take the mirror images of this compound, that will be again the identical compound. That is not the enantiomer, right? Okay, let's move to third compound. I hope first two compound is clear to you. Let's move to third compound. Third compound, if you observe from top side, the second chiral carbon is having similar configuration as in second. So here, if the S configuration is here in second chiral carbon, at second chiral carbon in second compound, then definitely look at the structure of second chiral carbon in compound 2 and 3. It is same. So S here, S will be here also, right? This is the way you can write the configuration bit faster way. Otherwise, you just decide the priority, look at the lowest priority position, lowest priority atom or group of atom position, and you start moving 1 to 2, 2 to 3. Use the rule. You can find the configuration from there also. Otherwise, use your mind, right? The second chiral carbon, it is having similar structure as the first one. First compound, second chiral carbon, it is having similar structure. You can observe. Look at the second chiral carbon, it is very similar to that one which is present in first compound. There it is, the configuration is S, so here it will be configuration is also S, right? You can find the configuration also, you are going to get the same. So, if it is asked, what is the relation between 1 and 3? Here it is RS and SS. Definitely these two can never be the mirror images. But these two are having same molecular formula, same structural formula. These two are stereoisomers. These two will be diastereomers. Diastereomers. So what I am saying, pair of 1 and 3 is diastereomers. Similarly, if you look at compound 2 and 3, 2 and 3 are also diastereomers. 2 and 3 are also diastereomers. SS configuration and SR configuration are going to be diastereomers. Now the next. Fourth compound is slightly different. This is different. OH group is drawn on above side. So you need to find the configuration here. OH is having first priority, H is having fourth priority, this CS3 is going to have second priority, and this complete group is going to have, this CS3 is going to have third priority, this complete group is going to have second priority, right? I'm doing this for the first chiral carbon. Look at the position of least priorities, it is on horizontal line, start moving first priority group to second priority group, then second to third. You are moving in anti-clockwise direction. So the configuration of this chiral carbon is going to be R, right? And the second chiral carbon, if you want to find the configuration of second chiral carbon, look at second chiral carbon, look at the structure, it is same, right? Here H, OH, H is on left side, OH is on right side, H left side, OH right side, CS3 down side. It is having R configuration, so it is also going to have R configuration. Next, if it is asked, what is the relation between 1 and 4? It is diastereomer. 1 and 4 diastereomer, R, S. Definitely they are not going to be the mirror images. 2 and 4 diastereomers. 3 and 4 it is SS and RR. It can happen only when you are going to take the mirror images. If you are going to take the mirror image of third compound, the configuration will get inverted, S will get converted to R. So here it is SS, and the next configuration in mirror image compound, the configuration is going to be RR. So what can I conclude? Compound 3 and 4 are mirror images. While if you look at the structure, it do not look like mirror image, but these two are mirror images, right? It can be seen. If you want to exactly observe how these two are going to be the mirror images, my suggestion is draw the Sohos projection of compound 3 and 4. And also remember one thing, by the rotation around single covalent bond. What I'm saying, if you will draw the Sohaus projection of third compound, there will be single covalent bond between carbon number 2 and 3, and we already know that around single covalent bond free rotation is possible. So just hold the one carbon atom and rotate the second carbon atom. Free rotation is possible around single covalent bond, and the statement is, by the rotation around single covalent bond, the compound is not going to change. But while taking the mirror images, it may get changed, right? So just draw the Sohaus projection of these two and try to rotate around second and third carbon atom. You will find that second and third and fourth compound are mirror images of each other. Or alternatively, what we can say, we know one thing that if even number of changes are done around chiral carbon, configuration will retain, and if odd number of changes are done around chiral carbon, configuration will get inverted. So do one thing, in the fourth compound around first chiral carbon, do two changes, because 2 is even, so configuration is not going to invert, it will again become R. So if you are going to do two changes, you will observe that compound 3 and 4 are mirror images. What are two changes? You can observe that just exchange this CS3 and OH first. Let me do that. You may get confused. What I am saying, I am doing this just to show you how these compound 3 and 4 are mirror images of each other. While on seeing at first sight, it looks different, right? So do one exchange between OH and CS3 around first chiral carbon. If you are going to do that, CS3 will be on top side, OH will be on right side, H will be on left side. And the next is second chiral carbon, keep it same. This is one change. Do one more change, exchange this H and OH, it is CS3, OH on left side, H on right side, rest portion is not affected, OH, H and CS3. What I have done, I have done two changes around first chiral carbon. So if it is having for R configuration, on doing even number of changes around chiral carbon, configuration will retain, it is also R. Second chiral carbon, I haven't changed anything, so it is also having R configuration. So this compound is having also R configuration. Now look at this compound number 3 and this final compound. These two are mirror images of each other, right? So this is how you can observe. If it is not seen at first sight, you can change the position of atom or group of atom. On doing even number of changes, the configuration is not going to be inverted. So better idea is do not do such type of things. That is just to explain, just to show you that compound is not changing, but these two are mirror images, right? So procedure is, just you need to find the configuration. If the original compound, if one of the compound is having a configuration SS and second compound is having RR configuration, definitely these two are going to be the mirror images. It may happen at first sight, it will be looking different, right? So next, move to the fifth compound. Again, find the configuration. If you are finding the configuration, I hope it is going to be S. Hard is OH is first priority, and this larger group is of second priority, and then CS3 is third priority. Lowest priority hydrogen is on horizontal line. So on moving 1 to 2 to 2 3, you are moving in clockwise direction, and lowest priority on horizontal line, configuration is S. Now the second chiral carbon, the configuration is going to be again S. It is going to be S. OH first priority, this larger group is second priority, and this CS3 is third priority. You are moving in anti-clockwise direction and lowest priority is on vertical line. For the second chiral carbon, the lowest priority is on vertical line. You are moving in anti-clockwise direction. The configuration is S. So the configuration of both the carbon is SS. Now, if you observe, 2, 4, 3, 4 was enantiomer, no? 3, 4. Write the enantiomers also. Enantiomers. 3, 4 are enantiomers. Now 1 and 5. 1 and 5 are diastereomer. 1 and 5 are diastereomers. Similarly, 2 and 5 are diastereomer. 3 and 5 are identical because both are having same configuration, SS over there, SS over here. It is 3 and 5 identical. 4 and 5 enantiomers. 4 and 5 enantiomers. Similarly, you can do for compound number 6 and 7 also, right? It's not difficult, it's easy. In examination, they are going to give you only two compounds, and they are going to ask what is the relation, whether the given compounds are diastereomer, enantiomers or identical, right? So let's do a bit faster way. OH first priority, then second priority, then third priority. You are moving in anti-clockwise direction, lowest priority on a vertical line, it is S. And OH first priority, second priority, and then third priority. You are moving in anti-clockwise direction, it is also S. So 1 and 6 are diastereomer. 1 and 6 diastereomer. 2 and 6 diastereomer. 3 and 6 identical. 3 and 6 identical. 4 and 6 are enantiomers. 4 and 6 enantiomers. 5 and 6 are identical. 5 and 6 are identical. The last one is 7th one. Find the configuration. It is S configuration of first chiral carbon. And for the second one, OH is the first priority, then move to second priority, then third priority. You are moving in clockwise direction, lowest priority is on horizontal line. It is S, it is also S. So 1 and 7 diastereomer, 2 and 7 diastereomer, 3 and 7 identical, 4 and 7 enantiomers, 5, 7 identical, 6, 7 identical, right? These are the answers for this question, right? In a single question, we can clear all the things related to diastereomer, enantiomers, and identical compound. There are two more definitions that we need to discuss. Let's start. Next definition. Next definition is racemic mixture. Racemic mixture. It is racemic mixture. Racemic mixture is equimolar mixture of two enantiomers. Take the two enantiomers, means optically active compound and mirror images of each other. Take the equal amount of these two compounds and mix them. That equimolar mixture of two enantiomers are known as racemic mixture. Equimolar mixture of two enantiomer are known as racemic mixture, right? Now, racemic mixture is optically inactive. Racemic mixture is optically inactive because two enantiomer rotate rotate PPL. We know that enantiomers are having different property, different behavior towards PPL. One is going to rotate the PPL in clockwise direction, while another enantiomer is going to rotate the PPL in anti-clockwise direction with the same magnitude. If one compound is rotating by 30 degree in clockwise direction, then its mirror image, if it is an enantiomer, will rotate the PPL in anti-clockwise direction by 30 degree. Right, so that I am writing racemic mixture is optically inactive because the two enantiomer rotate the PPL equally in opposite direction. Right, the cancellation of optical rotation is known as external compensation. External compensation means, let's see the example. If I have CH3, H, deuterium, F, there is one chiral carbon, compound is optically active, take the mirror image. It is CH3, H, deuterium and fluorine. We know that if it is dextro-rotatory, second is going to be levo-rotatory. If it is rotating the PPL by theta degree in clockwise, then second one is going to rotate the PPL by minus theta in anti-clockwise direction, right? So if you are going to mix these two compounds, because mixture of these two compounds is known as racemic mixture, so net optical rotation will become 0. One is rotating theta in clockwise, another one is rotating theta in anti-clockwise direction. So net rotation is going to be 0. This is known as external compensation because rotation of one compound is cancelled by another compound. That is why it is known as external compensation, right? Next, there are two more statements that we need to write. Let's write that also. The separation of dextro and levo from racemic mixture is known as resolution. Previously, what I was saying, if you are having a mixture of enantiomers, we cannot separate them by distillation method because their physical and chemical properties are same. We are having the racemic mixture, and from the racemic mixture, means racemic mixture is containing enantiomer, right? If you are separating dextro and levo, right, that process is known as resolution. And how we are going to separate the enantiomers from their mixture is also important, that I will discuss later. I can give you the basic idea that if you are having racemic mixture is containing dextro and levo compound, and you want to separate them, just do one thing. Do react with any external chemical compound so that these two enantiomers, we are having a mixture of enantiomers get converted into diastereomers. That is the basic idea. This is the way we can separate the dextro and levo from its mixture. If we can convert that enantiomeric mixture into diastereomeric mixture, just because diastereomers are having different physical and chemical property, now we can separate them. So I'll discuss that. I'll discuss the process exactly. What is the resolution, right? Let's write the next statement. There is one more statement. Mixing of dextro and levo to form racemic mixture is known as racemization. Mixing of dextro and levo is known as racemization. These are the some important points about racemic mixture. You should remember that. Next, we are left with the discussion of meso compound and calculation of number of optical isomers. Only these two portions are left in optical isomers. For today's class, this is it. I'll discuss the next part in next class, right? Do the assignment that I have given. That is compulsory. That will be better for you, right? Let's meet in next class. Bye bye.